So far, we've talked about the fact that since concrete starts out in that plastic state and then transforms to a hardened state, it makes a great building material. And in the last video, though, we talked about one of its limitations, being that even though it's strong in compression, it's relatively weak in tension. Even just increasing the concrete's overall strength or its compressive strength, like we discussed, results in very small jumps in that tensile strength. Now, in that segment, I did mention that there are things that we can do with the mix designs to create concrete with higher tensile strength. Again, we talked about using stronger aggregates or larger aggregates or adding more cement, taking out more water, and all of these things can be manipulated to change the properties of the concrete, but they also all have limitations. Now, don't get me wrong, as we invent more and more types of chemical admixtures and we push the limits of leveraging different pozzolanic materials, the industry is seeing more use of what we call high-performance concrete. And there's a great deal of research going on these days in the field of high-performance concrete, trying to make 10,000 or 20,000 psi concrete with incredible tensile strengths. Now, in the meantime, while all this research and development's going on, we do have a solution to the problem that's proven and dates back to France in the mid-1800s. Now, everything we've talked about so far, we've just looked at concrete used by itself. But all the way back in 1853, a French industrialist built what's considered to be the first iron-reinforced concrete building. It was a 4-story house in the suburbs of Paris. Now, in the 50 years that followed that, the idea of reinforced concrete was studied and published as a way to combine the high tensile strength of steel bars with that workability and high compressive strength of concrete. Now, this idea of reinforced concrete is used everywhere today by embedding steel reinforcing bars, and you might know these as rebar, into the plastic concrete. Now, this works really well because we can just put the rebar where it's needed when we're building the formwork, and then we can place the plastic concrete in the forms and around the reinforcing so that it all becomes embedded in that hardened concrete. Now, this actually works really well for a number of reasons. One, it's pretty easy to do. Two, concrete happens to bond really well to the steel, and that's important. 3, concrete is also highly alkaline, and what that means is when you surround the steel with it, it actually passivates that steel. It creates an environment that helps inhibit corrosion of the steel, so that's important. And then 4, the coefficients of thermal expansion of concrete and steel happen to be very similar. So these two products stay bonded together even when the heat and the cold affects the structure. Knowing these things, all we need to do to make this work is put enough steel in the right locations. Now, putting enough steel in is a matter for the design professional. They need to calculate the bending moments that are going to occur when wind hits a concrete wall or gravity pulls down on a concrete beam, and then put in enough steel in the design to get the strength that they need. Now, to get more strength, they can use larger diameter rebar, or they can just place more pieces closer together. But there are some limitations here, though, and one of those is that the steel has to fit inside the concrete, obviously, and another one is that the concrete has to be able to flow through and around the steel in order to cover and bond to it. Now, this is one of the reasons that designers may limit the size of the largest aggregate in the concrete mix. The largest aggregate, or the biggest rock, can't be bigger than the smallest rebar spacing, or it won't get through that grid of rebar. Now, as far as where to exactly place the rebar, this is also a matter for the structural designer. But we can get a good idea of where we expect to see the reinforcing or where we need the reinforcing by understanding where the tensile forces are going to affect that concrete member. Now, this is easy to visualize if we look at something like a cross-section of a supported concrete slab. Again, gravity is going to pull down this slab in the middle, and that effect is just going to increase as we put things on top of the slab. Now, since it's supported at both ends, it's going to end up trying to bend in the middle, and this is where I need my reinforcing steel. I want it in the middle, and I want it located down in the bottom portion of the slab where those tensile forces are trying to pull it apart due to the bending. Now, I've got the opposite condition over in the supports at the ends. As the slab bends and tries to pull itself apart in the middle, the tensile stresses at the ends occur near the top of the slab where it's supported. So in these locations, I would expect the rebar to be located in the top portion of the slab. Now you can visualize a concrete wall in much the same way. If it's a retaining wall, the forces trying to bend it are always coming from one side, with the tensile stresses occurring in the face that's bending. So I want my reinforcing over in this face. Now, on the other hand, if this were a freestanding wall, my loading could be coming in the form of wind from either direction. So in this case, I might have 2 layers of reinforcing, one in each face. All right, let's take a look at one last example here before we move on, and I want to visualize a concrete footing. Now, when I build a wall or a column from the ground up, I'm generally going to rest that concrete wall or column on a footing. Now, the footing's there to take all that weight and transfer it into the ground. That footing is going to be sized by the designer to spread that weight out, but as the footing gets larger, the potential for that wall or column to push on it so much that it bends goes up. So again, visualize where the bending would occur. We want the rebar in that bottom face where the concrete's being torn apart. That's where I'm going to locate my steel reinforcing. Now, all of this discussion also shows us one of the reasons that concrete cracks. When forces try to bend the concrete, it gets pulled apart. If those forces exceed the tensile strength of the concrete, it cracks. So we put rebar at these locations as reinforcing to limit those cracks and the effect that they have on the strength of the structure. But there is also another reason that concrete cracks, and that's a little harder to manage. So stick with me and let's take a look at that issue.